started today. Hello and welcome everyone to this webinar today, presented to you by Dassault Systèmes SolidWorks. Thank you all for taking some time out of your day to join us. On this webinar today, we have two presenters, myself, Sashi Sitambaram, and my longtime friend and co-worker, Joe Galliera, or better known as FlowJo. We both are work remotely in the Northeast area. I am located in the Western New York town of Rochester. And you can typically find Joe in the beautiful mountains of Vermont. So for today's webinar, we are going to be focusing on optimizing the design of compact CPU enclosures based on analyzing the heat distribution. So we do have a design challenge, and me and Joe are going to play the role of design simulation engineers in an engineering company. So we are going to try to design and optimize the best CPU enclosure for our make-believe company. At this point, I'm going to hand it off to Joe to talk about the design challenge and the initial simulation setup to investigate the airflow. Joe, go ahead.
Thank you, Sashi. So today's design challenge, as you can see, representations of the geometry that we're going to be working with today. And I want you to think of the constraints that we have that we want to model to. Okay, so first in the top right, we have a CPU that we want to maintain that is a max of 68 degrees Celsius. We have a package of integrated circuits that are connected to a customized heat sink, as well as some RAM chips along this board here, down to a maximum of 59 degrees Celsius for the chips, and the integrated circuit package is 95 degrees Celsius. So if you focus on the bottom right image, you can see some features, slots on the top here, and some holes for perforated plates that you would find typically in an electronic enclosure such as this. So one of the things that we can, a design consideration is to change the packaging. So we're going to look at how we can enable change that, as well as the number and configuration or the location of fans that we have on the outside here that are around where the circular perforated holes are. So our overall objective is to keep everything cool and minimize the heat buildup within this compact CPU enclosure. So I'm going to sit along the agenda today. I'm going to step you through the setup of the simulation and how you would interface it within the SolidWorks software. I'm going to go with you over some results with you and how you can visualize those and get some real numbers. And then we're going to together look at some design alternatives and seeing how the software can be used to facilitate that. So first, let me step through with you to the software by pulling up my SolidWorks interface here. And I will mention that once I'm working, as you can see, in the SolidWorks interface, and I can go to my configurations, which I'm working with the default configuration here, as you can see right now. And to do an analysis, I'm going to enable through this toolbar my Flow Simulation tab, which allows me to set up this, a study that I want to run. Now, I'm going to run with a simplified geometry using a configuration, and that's to facilitate the analysis. So a few things that I will mention is that we got rid of the holes, as you can see in the slots. We're going to be defining some modeling conventions that you would use in a thermal package like this to simplify it by using a pressure drop model, as you'll see, specifically called perforated plates. So this creates a watertight solid. So that is a watertight solid then facilitates the software to know where the voided region is, where the fluid would be within that. So there's no need of creating this fluid volume yourself. The software inherently knows it when you have, for an internal flow calculation, a watertight volume. Now, for an external flow, if you wanted to mimic also the air or simulate the air around the outside, we would do that by an external flow calculation. And in that case, the enclosure does not need to be watertight, but you change the computational domain, the size of the box that you want to simulate the calculation. So we can set up a new calculation by working from a template, and you can create, if you're working on similar types of projects all the time, a full template, which then you can just as a starting point and then use different geometry for that template. But I'm going to step you along in a wizard-based interface, and I'll call this just project name webinar 1. And I'm going to step you along in this process in defining the initial settings for the calculation. And we're just going to quickly go through this, selecting first our units. There's your standard predefined like SI or Imperial or USA units that you can choose from. But more often than not, we like to maybe do something that's customized to myself, what I like to use. So I have a mixed unit system that utilizes PSI, which I'm more familiar with, but we're also using degree C, as we saw in the definition of this problem. And there's a few other things that I've defined, and I name this to remind myself. So the fan flow rate is going to be in CFM, RPM instead of radians per second, and things like that. So you can customize the interface for your own usage. Now we're going to look at the physics of the problem. So is this an internal or an external flow? Right? So as I mentioned, we're going to be simulating this as an internal flow. We're going to include heat transfer in the solid, and we want to turn on gravity, right? And so gravity is in this vertical direction in the Y as we would like that to be. And we also mentioned that we have other thermal heat transfer methods such as radiation that you can include. So we're going to be doing both conduction and convection in this example, but if I wanted to, I could also include radiation. We do have locally and global rotating bodies. We can do free surface flow, and we can do transient analyses as well. If you just want to solve a problem over, say, 10 minutes and see what the results are after every 30 seconds, it would be as simple as defining these conditions as you're seeing on the screen right now. But this is going to be a steady state calculation for all the results that you see. So I'm going to disable that and move forward to my next case, where I'm going to define my fluids. So we have a whole library of fluids that live into a full library, as you can see here, of different types of things: perforated plates, porous media, and printed circuit boards, and other conditions that we can define. As you can see, air here being one of the temperature-dependent properties for specific heat, thermal conductivity, and what have you. So I'm going to add this air, and I will mention just real quickly that you can also define your own fluid properties through that library. I'm also going to enable humidity as part of this condition, and that will just change some of the conditions for that fluid, which I can set later in my initial conditions for the humidity of the environment. Since we're going to include solids in the body, we just want to make sure that every part within the model has a material property defined for it. It may not be defined in the SOLIDWORKS model, but we need to have it as part of the thermal simulation. So we have your standard metal materials, also a lot of different alloys like aluminum 6061. So I'm going to set that as my predefined solid. But actually, in fact, that 6061 alloy was defined in the SOLIDWORKS model, so I can reuse material properties that are defined in the model. So just making sure everything has a material property. In my default outer wall condition, so how am I dealing with, since this is an internal flow, what's going on outside, whether it's fully insulated, or I can define a heat transfer coefficient, a wall temperature, heat generation rate would be another condition. So we're just going to say that this is at 15 degrees C, which is also 59 degrees Fahrenheit, and say 8 watts per meter squared Kelvin for a heat transfer coefficient as an average value over the entire outside of that. Now, again, if you want to have more localized conditions, you could do that as an external calculation, right? So we're going to set here again our outside conditions. The humidity we'll just keep as 50%. Solid parameters, we can start that as an initial, same temperature as the other one. And this is just going to be sitting in stale, non-moving air. So those are my ambient conditions, or if you're running a transient, it would be your initial conditions. All right, so you can see within the interface here, some of the first things you see is the computational domain, which can be modified. We can do 3D as well as 2D simulations. On a given body, you can utilize symmetry or periodicity. So for example, since this is the same value, different sign, if I set the Z direction, here you can see that we're not, if this were symmetric from left to right in the Z direction, I don't have to change the SOLIDWORKS geometry. I can just change the computational domain and then set this condition here as being symmetric like that. And you can see it's, so it's a very nice interface of dealing with that. And I just hit the reset button to bring me back to the normal because I'm happy with this, and I'm just going to hide that condition as such. Now, to facilitate this webinar, just real quickly, I've already have some of this set up already for me with some of the conditions, and I'm just going to walk it through with you, adding some additional conditions. Now, note that this tree is customizable for things that you're going to often be using, but you can always go to the toolbar and insert any condition that you want that is specific to a project. So these are default things that are always going to be in the tree, or things you can add to that as needed. In your solid materials, we can import data from the model, as you saw, for all the parts. Or here we also can utilize our library, and I'm just going to choose an ABS material. I believe this is in ABS material for this enclosure on the outside, and then that gets added here to that tree item. Then we can define our boundary conditions. So we have inlet and outlet mass and volume flows, as well as Mach number. If, in this case, if we want to do a compressible flow problem, we could do that. And then we have pressure conditions, which I'm going to be defining, so I'll come back to that, as well as wall conditions. So, if there's some locally rough wall or temperature in the wall, or wall motion, if you want to define that, you can just set these as real walls, but we also have ideal walls and a different outer wall condition if you want to for this internal flow calculation. But I'm going to be defining an environmental pressure and utilizing, if we zoom up here to see what I'm doing, right click and select other, just like you would in SOLIDWORKS, to select these faces which were closed off, and then I can define these environmental pressure for those at 1 atmosphere is what that value is. So that was already defined. That's fine. I think I meant to define the slots, but you know what? This gives me the ability to show you a functionality real quickly here. So environmental pressure 2 is the ability to copy to a project these slots to the project that I am working on here, which is the partial setup problem, right? So if I go back to this new project, you can see that that was defined and copied for me there. All right, and then we have our fans. So we can define these fans, which are set up here. This is a they're on the outside, and they're only going to be blowing inside to the volume. We can have ones that are venting or fans that are set inside completely within the volume. So we have, this is the inlet fan, so I'm going to choose a face here, again using my selection tools to help me select the right face. And then I can choose from my library of fans my fan curve here. And just to show you how this is defined, because this is going to be applicable later, is just the real way in a fan curve how it behaves with your pressure drop in PSI versus your flow rate that it can deliver at that pressure differential. So we'll set that here for us and hit OK. All right. So we can do this for all the other ones. Again, just again copying this to my existing study. And then just assigning a new face for this is one way that you can do that. So just choosing that new face there. And then you can, using Windows functionality, copy that to there. And then we could define the other one in the same way very quickly. You can see that this interface allows you to do this quite easily. Oop, 3. Wrong one, that's okay. And then we have heat sources. So let me run through with you the heat sources that we have here. We have these 4 components. Each of them, since there's 1, 2, 3, 4, are a ¼ watt each. So we define these as a total. And since they each have the same volume, they're the same component, we can define them like so. We have 3 watts on all of 1, 2, 3, 4, 5, 6. There's 6, 12 total. 1, 2, 3, 4, 5. Sorry, 10 total. 3 watts. 40 degrees Celsius for these capacitors. These are 60 degrees C. And then 8 watts. Or actually 2 watts total. This name is incorrect on there. But these each have a ½ a watt defined for them. So I'm going to show you, we can define a surface or a volume, a heat source, right? And the real difference there is just how you want to define those. So I'm going to use my tree and select these 4 components like so, all right? So this would be one way in which you can do that, selecting them all and put in 4 watts for the total, right? But I'm going to do, let me clear this and make this only just a single, because there's another really nice functionality that I want to show you, is that if we define, let me see here. Okay, so let me just suppress this. I forgot which ones I was defining. So anyway, if I define this 1 watt for this, I can right click and again, apply that to all the other conditions there. All right, let me just skip over that. And how are we going to handle the perforated plates? So we have the slots that are on the top. All right, and let me just describe what this is doing. So instead of having the slots modeled, what we can do instead is define the free area ratio, how much of that air ratio allows flow to move through that, and that sets up a normal pressure drop, all right? So that's one way of doing it. Now, if we have something like small circular holes, which we're going to do on the back of this here, I'm going to pre-select this pressure 1, so those 3 faces, so pre-selecting that, utilizing information that I've already used, and then I'm going to choose this one with the circular holes. All right, because there's also an additional way that you can define these. Whoops. instead of a free area ratio, you can also define a pitch, right? So these are round holes with a given diameter, and you can then define the distance between them, say in the X and Y, and that gives you then a free area ratio. That should be like so. All right. Just coming down here to our other conditions that we're defining, we have a integrated circuit, a plastic ball grid array, 40 by 40, and we're defining this as a 2 resistor component, just to show you some of the details of this. So these are the components in which we're defining it to, as you can see selected here. The face that is connected to, it's the hot side that's connected to the heat sink, as you can see, and this is generating 15 watts of heat. And just a little bit of information about this specific plastic ball grid array. You can see that we're defining the 2 resistances, the junction to case, and then the junction, or case to junction, and then junction to board in that way, in that vertical definition. And we have printed circuit boards, where in this definition we are defining, these are already the dielectric or FR4 materials, the conductor or copper materials, and then we can set up in a table how many layers, what the thickness of the layers are, and how much of the copper conducting layers is on each one of those. And then it'll calculate the orthotropic material in plane and through the thickness, and also the effective density and specific heat for this 4-layer boards. So we have those printed circuit boards defined, and then the RAM boards defined in a different way. And then to set up what is important, the information that we want to get out directly from it, the calculation, as well as using these as convergence criteria, we can set goals either globally at a point on a surface, a volume or component goal, or defining an equation, say if we want to find pressure drop or other things. So defining a volume goal real quickly here. I can reutilize information, just choosing this and then selecting the RAM chips from that. All of those are populated here within my selection, and then I can choose my temperature of solid from this list down here and choosing the maximum value from this column right there. And then define a goal for each component. And that defines all of these, and I can rename those to be more descriptive. All right. So let's going back to the PowerPoint real quick, just to review this setup. So we set this up as an internal calculation with heat conduction in the solids, as well as gravity, setting up the air condition as our fluid, defining our environmental pressure condition, in addition the circular perforated plates, define that pressure drop as well as the fan condition, those 3 fans, setting up our heat generation rates as well as our printed circuit boards, and then we can run the simulation. All right, so Sasha will run through and show you a little bit more about how you can do multiple simulations, but if you're running just a single setup like this, you can run it on as many CPUs as your machine has. In this case, a quad core virtualized to 8. And you can see that it's utilizing all of those cores very effectively. We can run the simulation, and you can plot out and view the progress of these values as they're calculating and iterating along. Similarly, for a transient calculation, you can have the X being the physical time, and you can also visualize the results as they're calculating, either as contour plots or vectors. All right, so it gives you progress on the simulation. So let me just, really quickly, the setup is easy to use, it's embedded within SOLIDWORKS, and it does a very good job to allow you to set up your thermal problem. So let's take a look at what types of results that we can look at. Going back to our interface, let me go to this problem that is already solved and go to my results, and I'll just load those in. So we can show our cut plots. As you can see here, we have our temperature. Let me make this horizontal here and expand this a little bit so you can see this. And we have, the results everywhere in 3D. So you would only be able to see this type of information from a virtual simulation like this. Okay, so you can drag and drop that anywhere. You can also probe the results, right? So if we're interested in the temperature as well as maybe velocity in different locations, you can choose which parameters that you want to show. So I'm going to show the location of those points as well as the velocity at all of these, if that is applicable. Here you can see on my solid it's 0. We also have surface plots to show, say, the heat transfer coefficient on this heat sink, as well as combining this with our flow trajectories colored in a different color scheme from 0 to the maximum velocity. And I can play these flow trajectories to show how that is acting to cool down that heat sink. And you can see that only on the front face of that do you have the maximum cooling efficiency for that. All right, so you get a lot of different visualization capabilities, but we're not limited to just that. You can also take a look at those goal plots in greater detail, right? So insert a new goal plot, choosing all of those, and we can show those on the screen at the bottom here like this, either a summary of all of those values or a history of how they iterated and converged on those results. And we can also, we utilize Word, Office, Excel, and you can export that directly to here and set this up for the ways that you want to present the data to your clients and colleagues maybe within the department, okay? So there's a lot of great information that you can gather both visually and the data to understand the performance vividly. Now, in this situation, we noticed that there's a lot of room that we can improve the design on. So I'm going to hand this back over to Sashi, and he's going to lead you. Let's hand this ball over to Sashi, and he's going to lead you on these design alternatives that we can evaluate.
All right. Thank you, Joe. Okay. All right. So now that Joe has gone over the initial setup, and he has so this is a very typical in a design environment where you have your initial design and you set up your analysis with all the given components that you have within your enclosure, and then you proceed to run the first iteration just to see what's going on internally. And flow simulation gives you that idea, right? So now we have a better understanding of how the airflow is flowing through the perforated areas, how the air is flowing out of the vent, how we are cooling a lot of the components in the system. However, in a perfect world, you could probably say, okay, we're good to go. However, it's never a perfect world, right? So in a design environment, you might have other criteria outside of our heat flow analysis that we need to consider. So in our make-believe company, perhaps the manufacturing course of manufacturing this enclosure, it's a problem. So the engineering manager has come back to us and say, hey, the enclosure is good right now. However, we are breaking the bank for this the manufacturing cost of this enclosure, considering we have a lot of these holes as well as so these vent holes. So if we are able to remove some of these holes, so obviously the fan holes we obviously can't remove that. We might be able to reduce the number of fans. However, the first thing that comes to mind is the vent required for this enclosure? So that's what we're going to consider as a design alternative. Is we're going to remove the vents and rerun the exact analysis that Joe had set up in the first portion of this presentation, and we're going to see how does it affect the airflow. Are we creating any air pockets? Are we creating any heat zones? Any dead areas? So I'm going to switch over to SolidWorks and kind of pick up where Joe left off. So using SolidWorks, and this is really what's nice about flow simulation being fully integrated with SolidWorks, is that at any time we can go back and forth between the analysis environment and the design environment, right? So now we are taking a step back from the analysis environment and saying, okay, we're going to make a change to the actual design itself. So if we look at our configuration, we have several different designs within our configurations. So our previous design is we had external fans with vents, and if I just do a quick section plot, we can see how that vent was created here. And as Joe had mentioned before, this is a simplified model, so we don't actually have to model the actual vents itself by setting up the surface area as a perforated plate in a virtual environment, in an analysis environment. We're able to solve this much quicker. So here is the vent in question, and all we needed to do in SolidWorks was to suppress this feature right here of this voided area. So I'm just going to switch over my configuration to no vent, and you can see now those vents have been removed. Okay, so I'll just click that to turn off the section view, and we'll go back into our flow simulation projects. And in terms of running the analysis, we don't have to recreate the entire analysis, right? Because all we did here is we changed the design, but the majority of the design, and 99% of the design, still remains the same. So all we needed to do was just clone the original study that Joe had created. So and that can be done very easily. It's very similar to what Joe showed earlier in terms of copying to project. So for example, we have several different projects here. All we needed to do was just right click on the project. So this is the project with vent. So all you need to do is just right click the project and say clone. And we'll say select configuration, and you just select one. We can say external fans with no vent, and you can hit the green check mark, and it will create the project that looks just like this. And automatically the perforated plates for the vents would be suppressed, or you can just right click and delete it all together. Okay, so the analysis itself, we didn't have to make any changes, very quick and easy. All we needed to do at this point was right click the study and hit run, let the analysis run, and we can view the results. So we'll go ahead and jump right into the results. As Joe had showed earlier, the best way to see the changes or any type of airflow is to start with the flow trajectory. So I'm going to say show, and we can just play this just to get an idea of how the flow is moving now. So you can see right off the bat, the change is that the flow is no longer moving upwards in the vented area. It's moving right through the system, from the fans to the holes at the end here, the perforated holes. But the question is, are we still removing the heat, or the dissipated heat in the system as well as we did before? And the best way to do that is to really dive into the model. And there's several ways we can do that. We can either use a point parameter, maybe surface parameters. We can probe the model, and we can extract the information that we need. Now, we are mostly concerned about three main components, and I'm going to show you in a second. We have a graph showing exactly how what the temperature difference is with the vent versus no vent. But before we jump into that, I'll just show you the cut plots, so you'll be able to see it. And I'm just going to make this a transparency. And that's another nice additional feature of the integration, is that at any time I can select any of the components and make it transparent to really dive in and see what's going on in the analysis. So we can see here, we might have taken a screenshot of the previous analysis with the vents versus without the vents. And we can see how the air is distributing now in this system. So we'll switch back to my PowerPoint, and we can see the analysis with no vent versus with vent. So you can see how the air is flowing upwards versus the air moving directly through the system. So at this point, we might say, well, you know, it seems like we are pushing hot air onto other components versus having released hot air. But based on this view as well, we can see that there is some cold air being removed from the system through the vents. And this is due to the differential in pressure in the system now, because when we have the vents, we are reducing the amount of air pressure within the system versus no vents now. There's only really one airflow in this axis of from the inlet to the outlet. So let's take a look at the graphs that we have put together based on the no vents and with vents. And clearly with the vent, the CPU, the main CPU component, the temperature was much lower. And with no vent, the temperature was much higher. For the IC package, the difference in temperature was, I think, is not insignificant. It was not that much. It was a slight difference in temperature. However, for the RAM packages that we have, or the RAM chips that we have within the system, we actually saw a decrease in temperature with no vent. And the main reason to this would be that we are restricting cold air from being released out of the system. And now we're actually having a more consistent airflow throughout the system with no vents, and those RAM chips are now getting a good distribution of cold air as well. So at this point, we might still be considering, well, is no vent worth the cost, right? Of worth the extra added manufacturing cost. So not only with the vents, there's a few other things that we can consider here as well, right? So we say, okay, maybe we can go with no vent. However, can we still optimize perhaps the fan configuration to get the airflow as good as we did with the vents and all three fans blowing through the system? So Joe had showed earlier setting up 3 different fans, and there is a question of whether all 3 fans is required in the system. So there could be different requirements in your design environment. There could be a noise requirement, right? 3 fans might be very loud. We might need to reduce the number of fans. The position of the fans could be a requirement. And also 3 fans could potentially affect the airflow of the system, because now we have air intersecting each other. The differential in pressure within the system has changed. And again, going back to SolidWorks, we can easily test all these different configurations quickly. So what we have here is we have 3 fans, which we have labeled A, B, and C. So I'm going to quickly just go over the airflow or the flow trajectory, so you can just see how the air is flowing through the system for A, B, and C. And then we're going to go back to the PowerPoint and see the difference in results. So we will just activate this configuration, fan A. And I will say play. And here you can see that all we needed to do here to specify that this configuration is only blowing air through fan A and fan B and C is going to be turned off is just coming into the analysis and suppressing those 2 other fans. So you can see how easy it is to toggle between your different designs, right? So we have 3 fans. Now we're going to say, okay, we're going to just test for fan A and see how the air flows. And now we can see that there's a high airflow through this heatsink area right here. And I'm going to stop this. We'll look at fan B. And I'll just load the results here. Give me a second. And let's see the flow trajectory. And here is the flow trajectory for fan B. So you can see that we are creating somewhat of a whirlpool effect here. So a lot of cold air in this area. Not sure whether it's required in this sense. However, just to give you an idea of how we can quickly change the configurations to view the different airflows within the system, right? So now we are all this is still being done in a virtual environment. There's no prototypes that's being built yet, and we can use this different information to make the best design at the end of this process. So I'm going to stop this, and we will go back into the PowerPoint to see all the different configurations we have. So just to kind of give you a reminder again, so this was A, the first fan here, B was this middle fan, and C is this third fan. So A, B, and C is only fan A or fan B or fan C being turned on. Then we have another configuration with fan A and B turned on, fan A and C turned on, and fan B and C turned on. Now at this point you might be saying, well, there's quite a few analysis. It might take time to set up the analysis. Well, we already saw that cloning the analysis will help with that. We can very quickly just clone the analysis, suppress the fans, and run the analysis. But you might say, well, running 6 different analyses back to back might be time consuming. Well, in SolidWorks, we do have the ability to batch run our analysis. So if you go into our tools here, Flow Simulation, and look at Solve, we have this option here called batch run. Basically what batch run does is it will take all the analysis that you have pre-set up. So in this case, I can set up all the different fan configurations. And at the end of the day, when you leave to go home at the end of the workday, you can actually just batch run your analysis and say, run all this analysis back to back. And when you come back in the morning, you're going to have all these results ready to go for you to view and make those and to view the difference and compare the different configurations that you have to decide the best best assembly. So in addition to flow trajectory, because of the way we had set up our goals, there's many other results that we can also view in this analysis, such as your goal plots. So I'm just going to go back into this analysis right here, and you can say show. So here's a goal plot of this analysis, and we can extract information for example, the heat sink for all three different configurations, whether it's A, B, and C, using this graph. And all this information can be transferred to Excel format, so you can extract the max temperature, the minimum temperature for the analysis as well. And by compiling all this information, we can come back in here and we can graph something like this. So here we have again, so the three main components that we're concerned about is the CPU, the IC package, and the RAM chips. And we can see the different configurations that we have, where this is all three fans turned on. This is only fan A turned on, only fan B turned on, and so on. Now, clearly, when we have the air blowing from just in the first fan A here, this entire area where the CPU is located is being missed, right? So there's no direct airflow on that area, which we can see there's a spike in temperature. So this first configuration, A configuration, is probably not going to work, and we just take this out of the equation. However, if we look at some of the other configurations that we have here, such as perhaps D or C, we can see that the temperature is, or at least for the IC package, there's not much change in temperature. And also for the RAM chip, there's not a big change in temperature. However, there is a significant change of temperature for the CPU when the air is blowing directly on C. So here, what we've discovered or uncovered is that just C alone, one fan, could work for this analysis with no vent included. So let's go ahead and take a look at actual numbers. So we'll see here that the IC package, all our T max is all within the 90 range, so plus or minus 2 or 3 Celsius. And again, as I said before, that A fan is just out of the questions here, so we won't even consider that. However, the C fan, we are getting a temperature of 93 degrees, so it's probably about 3 degrees higher than the minimum temperature, where if we have a A and B or a B and C fan. But another thing that we have discovered here is that 2 fans is giving us better temperature than 3 fans. And Joe will kind of talk a little bit more about this as to why that's the case, right? Because you have 3 fans, maybe there's more airflow flowing to the system, so there should be a more cooler air, and why is the temperature going up, right? So these are the type of questions that might come up as you're designing this, and we're going to address that towards the end of this presentation. So just to summarize again, just fan C alone might be a good option, or fan B and C might be a good option. So looks like, fan B and C might be the best option here to go with. But again, considering noise, we might say, well, to meet the noise requirement, maybe we have to go down to 1 fan. And now we know that C would be the best option for that. Again, it all depends on your requirement. So just to kind of reiterate what we've done here, we removed the vent, so we were able to reduce the manufacturing cost of the enclosure. And we were able to reduce the number of fans that we were using in this system as well, which will then reduce the entire project cost for this enclosure. So evaluating multiple designs quickly, and we can use the batch run technique to set up all the different types of systems or different types of assemblies that you might want to consider, and run it all in one go when you're not present, and you can evaluate the results when you are present back at work. So at this point, I'm going to hand this back off to Joe, and he's going to wrap it up for us.
Thank you, Sashi. And that was an awesome way to really cover just a part of the power that flow simulation has. So we were able to, in this design challenge that we had, was to evaluate whether we have slots within our enclosure or not, and how that affects the results. Maybe from a manufacturing perspective, we want to remove those because it'll be more costly to include and have that additional machining or of the mold that creates that enclosure. So, and then also the fans, right? We're not just defining the maximum fan volume flow rate that a fan can define. We're using real fans and how they behave, and we showed through this comparison that fan that was right in front, the C fan right in front of the integrated circuit package with the heatsink, had the biggest impact on the design. Now, somebody might think that having all, say all 3 fans would be the best approach to do it. Add more fans, you're going to get more cooling, and that's not necessarily the case here. And what happens is that's a real effect of how these fans really operate. So having additional fans, while being noisier, they also create a higher pressure differential, and the fans actually don't deliver as much flow rate as they really could. So having a fewer number of fans in ideal locations gives you the best mix and optimal design. And this was all done in a virtual environment. So if we take a look at a summary of the benefits that we tried to share with you today, is one, that having this flow simulation software embedded within your SOLIDWORKS design package allows you to do things that are already familiar to you, as using configurations. And so it's really easy to use setup, and it also is defined in a way that is using terms that are familiar with design engineers. We can efficiently set up multiple design considerations for a thermal analysis problem, showing you many of the different ways that we can do that with perforated plates, integrated circuits, PCB definitions, cloning, copying, and also we didn't have a chance to show you our parametric study tool, as well as optimization tool that we also offer. So those all are different design variations that you can do very easily. And then Sashi did a great job in showing you how you can use our tools to compare the designs graphically, as well as with actual physical numbers. So all of this was done in a virtual design environment without having to create any components, and I think that is the best way of attacking a problem when you can easily make changes within your SOLIDWORKS design environment. So I wanted to thank you all, and if you stick around, we're coming up on the hour, but we do have some time to answer some questions, which we both tried to do during the presentation when one of us was not speaking. So that we just maybe would want to cover some of those questions. And actually, Sashi, I might take control back of the software, because there's one good question that I had to skip specifically because I didn't have time to cover it. But it was about the mesher. So Jack asked, can the mesher be handled to capture the heat sink, for example? So the way that I answered this and you all got a copy of it, is that it's a good question, but the software is able to capture any complex geometry that you can throw at it. It starts as it's a fully hexahedral mesh aligned with a global coordinate system, and the software uses a proprietary cut cell technique to both follow the geometry as well as handle the near wall boundary layer within cells that are called partial cells that cut solid and fluid there. The mesh will refine itself automatically based on small geometry features and curved bodies where it's needed. But also you can create local mesh controls that the user can manually define. So there are automated methods to set different levels of the mesh refinement if you want those, but also there's ways of unlocking and creating manual mesh techniques, including local mesh controls. Lastly, I just want to mention that the mesh does have adaptive mesh refinement algorithms. So while it's solving, it can refine the mesh to the high gradient areas to capture those. That may not have any geometry around it initially, like in the fluid volume, it can refine the mesh around high gradients of pressure, temperature, velocity, so forth. Eric asked the question, how do you get the Tmax out of each of the components? That is, we showed you in the goals and the setup, selecting the volumes or components that you want to define those goals for, and then just selecting from the table of values the maximum value of solid temperature. And then that gives you feedback while it's solving, as well as being able to very quickly create charts that you can either show in the software or export to an Excel template that is already predefined by the software for you. There was nothing that needed to be done. How do you get an average, Amit is asking the question, how do you get an average value of any surface parameter at any surface? Well, so this is why I transferred over to my screen here. Let me dock this and stop this animation here. And I can show you that if there was something that you didn't already define as a goal, so goals, you can define a surface goal, right? And you're asking about the average value. There's also in the results, if you surface parameters as well as volume parameters, so you can insert those after the fact and get an average temperature on a component. You can just choose, on this face, for example, and those values, if I choose even all here, just kind of give you, if I show this, it's calculating it now, it'll give you all the pertinent values for this. And these are, in terms of the fluid area, these are integral parameters. I guess I could add a parameter here. I was going to show you how you can add other parameters in addition to that if you wanted to get the volume flow rate and things like that, mass flow rate, if that wasn't in this list as shown here. Oh, and then also in the mesher, just to show you that kind of is the global mesh setting here was defined with an automated a manual setting of defining the number of cells in a given direction. All right, so you can do that, or setting the size of the cell in the X direction. Also, there's a way of controlling through different planes, breaking that up into several volumes in an X direction or any one of the directions. You can do that. And then, refinements within there. All right, this is the automated mesher, choosing different levels, which does basically some of the same things. Small gap sizes, you want to capture those. So if the size between the fins was, say, 1 millimeter, it'll make sure it refines it within that region. And then also, just to show you a local mesh setting, this can be done through any geometry that you can create that will be disabled, or you can create primitive geometry just using, say, this box if I were to capture this box around the heat sink, you know, I'm just doing it very quickly, and then we can define, you know, how many cells to cut that initial basic mesh down, and other channels and refinement techniques like that in a local mesh setting as such. Okay.
So the next question here is to why not simulate an exhaust fan? Alex is asking that question, and you absolutely can. So there can be instances where you model an external fan on the outlet, perhaps a centrifugal fan that basically pulls the air in the intended direction from the inlet fans. So it's just the way we have set up this analysis. We don't have an exhaust fan, but that is something that you can set up in your analysis.
Here, I'll take the next question here, which is how can we determine where the fan is on the fan curve with the system resistance? And yeah, so you could, one of two ways you can do it from the system resistance using an equation goal. You can find out what the pressure drop is from the inlet to the outlet to determine it like that, or you can actually just get the volume flow rate from that fan surface, and is another way to determine where that is on the fan curve. So good question, Rusty. Thank you. So there's many other questions here that maybe we won't have time to get to all of these right now, but we will follow up. We'll get all these questions and we can email the individuals who answered these questions. And hopefully you got a lot of value out of this webinar. So both Sashi and myself, we would like to thank you for, again, taking the time to join us for this webinar, and we wish that you all have a great afternoon.